My name is Huda Haida. I'm an astrophysics PhD student at Newcastle University. I am originally from Morocco, born and raised, and I decided that I want to learn more about space. So I moved to England for my PhD at Newcastle University, where I'm currently based.
I'm David Rosario. I'm a senior lecturer here at Newcastle University in astrophysics. I've studied in India and the United States for my PhD, and now finally I'm here in the northeast of England.
I study supermassive black holes, which are these giant monsters that are lurking in the center of most massive galaxies that we're able to observe. And my job is to try to understand or figure out how these monsters are ejecting so much energy and how that energy is affecting their surroundings. And I'm piecing all of this together using one of the best telescopes we have, which is the James Webb Space Telescope.
The James Webb Space Telescope is, in my mind, the most amazing telescope in the solar system, right? It is the newest thing. It is the largest telescope that's been put in space.
It was launched on Christmas Day, 2021. And it actually had more single-point failures than the Apollo mission, which made it a true Christmas miracle. So what's really exciting about the James Webb Space Telescope is that it can see light in the infrared. And what that means is that the universe almost becomes transparent to us.
In particular, it can find the furthest galaxies, the first galaxies that ever formed. And also, it allows us to understand what's happening in the atmosphere of distant planets, not our own, but planets around other stars.
Although we can achieve so much from ground-based telescopes, we always have the struggle of the atmosphere. Once we put telescopes up in space, we don't have the worry about atmospheric turbulence, and we can just enjoy beautiful, clean images.
So I'm studying something called dust. Which is what the James Webb Space Telescope is really good at seeing. It's the picking out hot, glowing dust. Dust is made up of, we call heavier elements like carbon or silicon, nitrogen, oxygen, calcium, magnesium, all of these very interesting elements. That's what we are made of. So to an astronomer, we are made of dust. And so how dust moves around in galaxies is an important part of where planets form, how we formed as well. So understanding the nature of life and planets and star formation in a galaxy is connected to how dust is blown out by supermassive black holes. That's exactly what I'm trying to do. I'm trying to use the James Webb Space Telescope to find dust that is being blown out and heated by a supermassive black hole.
My name's Ishbel Carlisle, and I'm a PhD student between Northumbria and Newcastle University. My research is on the aurora. The aurora is this beautiful, big sort of natural phenomenon that happens because the sun throws all of these charged particles or plasma from the sun, and it comes and interacts with our magnetic field. And our magnetic field is really good for that because if our magnetic field wasn't there, it would just interact with the ground because it's got this little shield all around us. And this little shield actually does magnetically attract these particles and accelerates them to the top or bottom of the Earth. And as these particles have been accelerated as they travel through, they crash into our atmosphere. And that causes the particles of our atmosphere to glow because they've got given a boost of energy, which is why the aurora is mostly green, because that's what oxygen does when it gets excited. It glows green. And we also get these blues and these purples from nitrogen and little bits of red from oxygen as well. But that's why it only happens at the top and bottom of our atmosphere, because it has to happen where there's the strongest magnetic field area going on.
My name's Professor Raymond Scullion. I'm a professor of space technology at Northumbria University. I did a degree in theoretical physics, and that evolved into a PhD in solar physics. So I came from a sort of a blue skies research background and not technological at all. But what motivated me was the potential to use CubeSats for understanding the solar atmosphere. So the sun spews out these large bubbles of plasma that collide with Earth and create things like the aurora and the northern lights, but they cause all kinds of radio blackouts and geomagnetic disturbances. And so they're hazardous, and that has all kinds of impacts globally.
As we're sending more and more satellites into space, they're sitting a lot higher above the ground than they used to. They're sitting in area of space that's not as protected by our natural magnetic field. And so there's a lot more charged particles running around. There's a lot more things that we don't always understand kicking about up there. And they can interact with these satellites because our satellites are, electrical. And if you've got magnetic fields and electric fields corrupting that, then your satellites might not be able to work out where they're going anymore. They might drop out of the sky. They might crash into other things. And the more we send up, the more it is important to understand exactly what's going on so we can mitigate against this.
So we need to be able to forecast those. So we need to be able to have satellites that can predict when those events are going to occur. And so I was fascinated by the need to continually develop the technology to do that better and better in order to be able to more accurately predict when these events would occur. So what we're working on at the moment in Northumbria is the development of small laser communications devices. So traditionally, satellites communicate with each other and with the ground using radio transmitters. And because of the huge distances involved, over 1,000 kilometers, the data rates are very low. But with lasers, because the energy is directed and focused, you can get very high speeds over very long distances. So we're building terminals to fit inside these shoeboxes that can transmit lasers between satellites. So eventually the internet will be in space. That's the future.
So I'm Patrick O'Neill. I'm a PhD student here at Newcastle University. I'm from around here. I was born in a little town called Chesley Street, somewhere between Newcastle and Durham. What I look at are these objects called neutron stars. And at the end of a star's lifetime, when it runs out of fuel, you can be left with this remnant called a neutron star. And these are incredibly magnetic, and they can rotate incredibly quickly as well. So fast, in fact, that a day on one of these stars would actually be up to 1/1000th of a second. This immense rotation drives these huge electromagnetic beams from the poles. And as these beams follow the rotation of the pulsar, we can actually see them when they pass over the Earth. By counting the pulses, we can infer a lot of things about the lifetime of a neutron star. We can even learn things about the expansion of the universe from that. We use these huge, enormous, 100-meter radio telescopes. For example, the one that was used in James Bond, there's the Arecibo telescope that, in fact, I've used data from, which is really exciting for me. And what we look for is this periodic signal. So when the pulsar rotates, then the beam crosses us. Just like a lighthouse, we'll see these pulsations, and that's where they get their name from, pulsars.
I'm Dr. Chris Harrison. I grew up near Middlesbrough, and I'm a lecturer and an astronomer from Newcastle University.
Hi, I'm Rose Shepherd. I'm a first-year PhD student at Newcastle University. My research project is about exploring the universe using sound. Specifically, I'm going to be testing if we can use sound to identify growing supermassive black holes. We observe the objects using telescopes, and from the object in the sky, whether it's a star or a galaxy, we collect a spectrum of wavelengths of light, all the different light that we can observe, and then we transform these into frequencies which we can then hear as a sound and play the different sounds that you hear from each of these objects and listen to how they sound different. Using sound to explore data it's a new technique that hasn't really been done before, and exploring data in a new way means that we can hopefully make some new scientific discoveries.
A few years ago, I met a very inspiring person called Dr. Nick Bond. He's blind and he's an astronomer, and he was showing me different ways to explore the universe. He'd created some tactile images of the universe, pictures of galaxies, pictures of stars that he'd made 3D so he could touch them. And that really got me thinking, we don't just have to use our eyes to explore space, we can use our other senses as well.
But another great thing about sonification is we can use it to make immersive and engaging public engagement tools and educational resources which are accessible to everyone, because traditional methods of visualization aren't universally accessible, especially to the blind and vision impaired community. So it's really important to be developing new techniques like sonification, which can help hopefully inspire a wider audience of people to get into astronomy.
As part of this PhD, I've also had a lot of time working on public engagement and outreach projects, one of which was Audio Universe. When we go into these schools with the Audio Universe workshops, it's been really, really good because you can actually, honestly, I get taken aback by it as well, but hearing things like the moon orbit around you, like physically the sound moving around you in 3D space, is you see the look on the kids' faces as they're like kind of shocked by the fact that this is something we can do, and it's the look of bewilderment for them is really like nice to see for me.
My name is Dr. Saunak Bose, and I'm an astronomer and associate professor of physics at Durham University.
I'm Beth Gold. I'm a PhD student in cosmology at Newcastle University.
I'm Sudikun Kunkor. I'm a PhD student at Durham University.
So my research studies some of the most fundamental questions about our universe. How did it form? When did the stars and galaxies form? Why does the universe look the way it does? What is it made of, and what might its end fate be?
Cosmology is a field study that we want to understand how the universe is formed, how the universe is created, to study how the galaxies are formed or the large-scale structure in the universe. With our understanding of gravity or the particle physics, we want to combine those two and understand the whole universe.
So the universe is, of course, made of the normal matter, the atoms and the molecules that we are familiar with. But one of the most extraordinary discoveries that we have made in the last 50 years or so is that everything that we know of, that we can see, feel, taste, and touch, and everything that makes up the periodic table of elements, constitutes only about 5% of all that is out there. It turns out that another 25% of this is in the form of what we call dark matter, so essentially things like our ordinary matter, but stuff that we don't actually see because it doesn't interact with light. And everything else, so the remaining 70%, is something even more mysterious called dark energy, which we think is actually responsible for the reason why our universe not only gets bigger, but actually is accelerating in its size over time.
If we look at the universe on the larger scales that we can see, the galaxies arrange themselves into a vast structure that we call the cosmic web, which is made out of filaments and nodes and huge voids in between. And we know that most of the matter in the universe is not the luminous galaxies that we can see. It's this other thing called dark matter. So galaxies really sit on this invisible cosmic web like iron filings on the lines of a magnetic field. So by understanding the way that the distributions of galaxies and the distribution of dark matter are connected, we can understand why the universe looks the way it does and start to get grips of the fundamental physics that underpins the cosmos around us. Over the next decade, telescopes like Euclid and LSST at the Vera Rubin Observatory will measure the positions of billions of galaxies, and because the farther out into space we look, the further back in time we're looking, this gives us a kind of motion picture of the growth of structure in the universe going back about 10 billion years.
With James Webb Space Telescope and Euclid Space Telescope, we'll be able to see the universe that we haven't seen before. We're going to see more incredible data with deeper survey.
With this new smorgasbord of data, we can start to answer these questions, and it's going to really drive a revolution in our understanding of the cosmos around us.
My name is Anjeri. I'm an astronomer at Newcastle University, and my background is radio astronomy. So you have the electromagnetic spectrum. So we have different lights, if I put it like that. For example, right now we are using the optical light, visible light, which enables us to see each other. So we have at the far end of the electromagnetic spectrum, so you have gamma rays, X-rays, all the way to radio. And what makes radio astronomy fascinating is the fact that radio observations remain unaffected by the dust and the gas in the interstellar medium, and therefore radio provides us with an biased or unobscured view of the objects in the universe. My specialty, or I specialize in the technique called radio interferometry. So radio interferometry is a very complicated technique that involves combining multiple radio telescopes spread across the world, observing a single object in the sky simultaneously at the same time. So you see, using this technique, we're able to create one huge, giant radio telescope without having to physically construct one. And this gives us this huge telescope, the size of the Earth's diameter, that is the Event Horizon Telescope. And they constructed this telescope by combining antennas or radio telescopes in Europe, North America, South America, Hawaii, Antarctica, to form this huge, powerful radio telescope with a very high resolution. And by using this powerful radio telescope, astronomers were able to produce the first ever image of a supermassive black hole. That is the supermassive black hole in the center of the M87 galaxy system. And therefore, you see that radio interferometry is a very powerful technique that enables us to observe these elusive objects in the universe, such as black holes.
Hi, I'm Vicky. I'm an astronomer at Newcastle University. My position is I'm a postdoctoral research associate, and I like to work on extremely bright galaxies that are powered by supermassive black holes. So I've always been really involved in science communication, so talking to the public about astronomy. I find that to get people interested in physics and also STEM, talking about space really gets people enthusiastic. So I think most people on some level look up at the night sky and they're really interested in space and kind of what is beyond there. So I go to a lot of schools, give talks about black holes because children love black holes, and then organise projects a little bit like this one, the museum exhibition, to try and get the public more enthusiastic about astronomy. In particular, I try and get girls more enthusiastic into astronomy because I think there's a lot of barriers in place. The things are getting better, but there's still some barriers in place for women to get into physics. So I like to go out there and show that women can do physics, women are good at physics, trying to get more women into physics.
So I'm engaged in several outreach programs. The closest one to my heart is Native Scientists, where it's an organization that allows scientists that speak other languages besides English to sort of meet underrepresented children and show them that you can be a scientist even though you come, for example, for me, I'm from Morocco, I speak Arabic, so not all scientists speak English and you can speak other languages. And again, science is a unified language in itself and it doesn't have to be specifically in one language.
I have this project I'm running back home. It's called Elimisha Msichana, Elimisha Jamii na Astronomia. That is Swahili. It's educate a girl, educate the entire community using astronomy. And the key thing or the main objective for the project is to ensure that girls stay in school. We want to ensure that girls complete secondary education. And the reason why I'm saying this is with my background, I realized most girls in rural regions of Kenya, not just Kenya, but the entire sub-Saharan Africa, they don't complete secondary education. So I've always wanted to do something about that. And my background being astronomy, I thought, wow, I could use astronomy to kind of create a change and have an impact on the community. We have a number of programs within the project. So a few programs include outreach, astronomy outreach and mentorship. So this is where we carry out astronomy outreach in several schools. We talk to the girls, we mentor the girls, and these are the girls in the lower classes to encourage them to stay in school and also discuss these issues that affect them and how they can not just the girls, but even the entire community, how they can ensure that these girls complete secondary education. We organize like very hands-on physics experiments for high school girls, and then we also have career mentorship for STEM subjects, basically encouraging more girls to participate in STEM. And the key objective for this is that we want to increase the number of girls pursuing STEM beyond high school. So far we've had tremendous success, and yeah, more girls are taking up physics back home.
I'm Cyril Bourgeneau, working at the Center for Advanced Instrumentation at Durham University.
I'm Katie. I am a postdoctoral researcher at the Center for Advanced Instrumentation at Durham University. I'm originally from Oxford, but I've been based in Durham for 10 years now. My research is all about trying to improve ground-based astronomy. So one of the biggest challenges with observing from the ground is that as starlight passes through the atmosphere, turbulence in the atmosphere distorts the light, causing it to twinkle. So actually, if we observe stars from space, they don't twinkle at all. So it's all just effects of the Earth's atmosphere. And this is a really big problem for doing ground-based astronomy because it adds noise to our measurements. So my research is all about trying to develop techniques to measure and correct this effect so that we can try and make ground-based observations as good as those in space.
Basically, if you want to do astronomy and having the best possible images, the only way is to either send a telescope into space, and you will know that Hubble Space Telescope, the James Webb are really producing stunning images because you are above the atmosphere. But it's not so easy to send telescopes. It's very expensive as well. So the idea is to build huge telescope that you won't be able to send into space. For example, the ELT, which is 39 meters. But because of the size of this mirror, you are actually subject to seeing all these little turbulences in the air. So being able to use adaptive optics offer the astronomer the opportunity to actually correct for these distortions and getting an image of the same quality of an image which comes from space.
One of the techniques I've developed is basically a way of correcting this twinkling of the stars. And the way we do that is we look at multiple different stars in different directions to kind of probe the atmosphere. And based on the geometry of where the stars are and the measured overlap at different kind of heights within the atmosphere, we can use this technique called tomography to basically produce a 3D model of what the atmosphere is doing above our telescope. And if we know what the atmosphere looks like, then we can correct for it. So through doing that, we can literally de-twinkle the stars.
Most of the telescopes have lasers now. It's to produce an artificial star So if you shine a laser into the upper layer of the atmosphere, there's a layer of sodium which is going to shine like a star. And then by looking at this light, you can actually compensate for the optical turbulences. Now, adaptive optics can also be applied to other fields, such as optical communications, because when you send a laser beam through the atmosphere, you will also be subject to the same turbulences. And by using adaptive optics, you can actually improve the communication systems. So I think there's a lot of potential using adaptive optics for free space optical communications.
So my favorite thing about working in astronomy is getting to go and actually use the telescopes. So I'm really lucky that in my research I get to go out to the observatories. So during my PhD I got to go to La Palma and I got to use the Isaac Newton telescope, which is this massive 2.5-meter telescope with so much history. It's so iconic, and I was able to just point it wherever I wanted. So that was really cool, really amazing.
It's getting to think about space every day, really. Like, to work in astronomy is to be surrounded every day by people who are passionate and knowledgeable about space and working together to find out more about it. It's pretty great.
Astronomy's been evolving for a long time, fairly slowly, and we've just hit a moment in space and time that it's exploding. Suddenly everything is changing in astronomy, which is, it's a bit breathtaking. It's really interesting that so many of our long-held theories about the universe, especially the distant universe, are folding and dissipating. They're being blown away by new evidence, both from James Webb and from other observations like the gravitational wave experiments, where we're fundamentally changing our understanding of where we are in the universe in a way that hasn't happened for maybe 100 years. So we're right in the midst of this revolution in our understanding, which is as difficult and awe-inspiring for us as anyone else outside of the field to try and grasp and understand, really.
One of the really cool things about being an astronomer is this amazing community all over the world. So for 3 years of my PhD, I actually lived in Germany at the headquarters of the European Southern Observatory, who are responsible for building some of these biggest telescopes. I also had the opportunity to go to Chile to observe using some of these telescopes. And these telescopes are in the desert, high on the mountain. It's an incredible place. The night sky looks beautiful, and you just feel so remote and connected with space.
I do a lot of outreach because I have a second job working up at Kielder Observatory. Kielder Observatory is a public observatory up in Kielder Forest, which is one of the most remote villages in the entirety of the UK, which means it's really far away from any light pollution. So it's actually some of the darkest skies in Europe are there. We get to look at planets and galaxies and star clusters and nebulae and all those really cool things that you wouldn't normally get to do if you just had a little telescope in your back garden. Sometimes you need this big equipment, but not everyone can afford to have that in their back garden. So it's really cool that there's a public observatory that you can just go to and get to do that and be with people who are extremely enthusiastic about it all and telling you and understanding all the stuff about it. It's such a cool and inspiring place to work. And so I get to do a lot of talks and outreach with the public, and it's just so cool getting to inspire people to look up and to feel really special and really small all at the same time and think about our significance in the universe and forget their problems and just sort of feel at one with the cosmos for a bit.
My name's Samuel Ward. I'm a final year PhD student here at Newcastle University. My research focus is on looking at how supermassive black holes affect galaxies. And in particular, I use computer simulations to study this. Simulations are really cool because when we make an observation of a galaxy, it can look beautiful, but because things in space are so big, it takes a huge amount of time for anything to change. So it's like trying to work out what's happening from a movie from just having one screenshot. But the cool thing about simulations is we can look at the range of time. We can make a model of a galaxy, see how it evolves with time, see how this black hole interacts with the galaxy, and then try to piece together what one single snapshot of an observation can tell us about how the galaxy is evolving.
In my research, what I do is to make use of supercomputers to actually create virtual replicas of the universe, where we essentially teach a computer how to solve the laws of physics and predict a replica of a universe on a desktop. We can then take that, compare that with the real universe, and see how well we've actually understood where we came from.
So instead of look at an image of galaxy, we want to build a galaxy from scratch, where we know how the particles inside the galaxy moves. So we want to solve those equations to match the real universe. That's how computational cosmology or computational astrophysics work.
So a supercomputer is basically just like an ordinary computer, but it's several thousands of ordinary computers all working together to solve a singular problem. So it's essentially tens of thousands, hundreds of thousands of CPUs trying to solve, say, the laws of gravity and make predictions for how things would move if the laws of gravity were as written down by Isaac Newton or Albert Einstein, for instance.
I'm Tom Stallard. I'm Professor of Planetary Astronomy at Northumbria University. I use telescopes to look at the upper atmospheres of planets in the solar system, mostly giant planets, so Jupiter, Saturn, Uranus and Neptune. The focus of the work is to look at the outermost layer of the atmosphere. It's a very thin and transient layer of the atmosphere, which, you know, in comparison to the bulk of the atmosphere is relatively unimportant, except if you're looking at the atmospheres and trying to understand how they evolve, it's that outermost layer that the atmosphere is lost from. So suddenly it becomes really important. If you want to understand evolution of planets over long periods, how they change over the history of a star, it's that layer that's super important. So it's really important to understand the energy in those systems. Everyone knows about the aurora at Earth. These planets also have aurora. So it's that interaction between the surrounding space environment and the top layer of that atmosphere that really drives the energy in those systems. And understanding that is difficult, but super important, because ultimately that's the region that controls how these planets change and evolve over billions of years. Amongst the many different ways you can use James Webb, we can look at Jupiter both with imaging and a spectral imager, which splits the light up into multiple wavelengths, and that allows us to explore all sorts of different aspects of the planet. You know, a lot of people might think, why are we looking at an object you can see with your eyes with the world's best telescope? It should be able to see everything really clearly, but there's all sorts of interesting chemistry that is hidden away and difficult to get to, including the upper atmosphere. The upper atmosphere is so weak and transient that we need something incredibly powerful to pick it apart. Something that's really interesting, when you look at James Webb images of Jupiter, they produce this huge wealth of new information. You could see the aurora at the poles, you could see a dark halo on the night side limb, which none of us expected to be able to resolve. And it actually pushed us as a community to propose new observations to explore that thin glowing layer on the edge, which is the upper atmosphere that we look at. And so we're getting this new view of planets that we've seen for thousands of years in a startling way that is unique to that telescope that is not only more powerful, but is able to see wavelengths that we don't see.
There are so many big unanswered questions about the universe. Is there other life out there beyond the Earth? What's this mysterious dark matter? How was the universe first created? And I'm so excited because over the next few years, there are huge new observatories and telescopes being built. And I'm feeling really optimistic that some of these big questions are going to be answered very soon.
So looking ahead in the next 2 decades, I think astronomy will really be defined by two groundbreaking instruments, the James Webb Space Telescope and the Extremely Large Telescope, currently being built in Chile. What's fascinating is to think about the kids now in school will be the next generation of astronomer, will be the one actually unleashing the potential of the data captured by these exceptional telescopes.
So for me, it might sound a bit cliche, but I know the next generation of telescopes, which will let us, as everyone will say, they can let us see further and resolve fainter objects out there. But really what excites me about it is, with all of this new higher quality data coming in, we need to really improve our theoretical models to describe it. So this really opens up for a lot of exotic modeling and interesting concepts to be explored. So really the limit is up to the imagination.
So I'm probably most excited about the prospect of finding life on another planet. So we've got so many more advancements in technology and instrumentation and also processing techniques that I think that soon we'll be able to find more Earth-like planets and hopefully actually show that there is life beyond our solar system.
I have this abiding desire to be alive in astronomy when we find the first evidence of extraterrestrial biology around another planet. We have a lot of tools and telescopes that are actually being used for this now. They're being designed in the next few decades to address this specific question. So I'm holding my breath for this, because it'd be a game changer for society, I think. I mean, life might not matter maybe in the grand scheme of the universe, but boy, for us, it matters so much because we are alive. I think it will profoundly change the way that humans think. And I want to be there when this happens.